Morning, my dear students. So in this class I am a continuation of the force vibration numerical problems I'm going to solve here. So topic is transverse vibration. So I told you what you mean by transverse vibration means what. Here the axis of the shaft can be rotated and perpendicular to the axis of the shaft is called as transverse vibration. Okay, otherwise take any disc or any rotated component that should be rotated, that should be vibration takes place perpendicular to the axis of the shaft is called as what, transverse vibration. Okay, so in this class I'm going to solve the problems on transverse vibration with different several loads. Okay, n number of forces going to act upon particular beam or shaft. Okay, that how to we are going to find the natural frequency of that particular component. Okay, so that we are going to solve in this class. Okay, so this is very important. So topic is what, the problems on transverse vibration with several load. Okay, different number of loads. Okay, so here I will give the question for what problem. I will read the problem here. Okay, a hollow circular shaft is given. Okay, one hollow circular shaft of an external diameter is 80 mm and internal diameter of 60 mm and 1.8 mm long is supported by a short bearing at the ends, and the shaft carries the two rotors, okay, each having 50 kg mass at a 0.6 meter and the 60 kg at 1.5, okay, from the left side of the shaft as shown in the below, that is given figure. Okay, that here the given figure. Okay, so the given I shown in the diagram here. Okay, given sugar, the density of the shaft material is 7, that is what, 7800 kg per meter cube, and the modulus of velocity E is equal to 200 giganewton per meter square. Okay, find the fundamental natural frequency of the transverse vibration, okay, acting on the forces of different several load or particular on that element. Okay, so here I will explain this problem. So one hollow cylinder is given. Okay, there is a hollow cylinder shaft is given upon which a shaft can be connected, that is the two forces are acting, that is, okay, one having a mass of 50 kg at a distance of 0.6 and one more is having a 60 kg at a distance of 1.5, okay, from the left hand side of the shaft. Okay, and they also given the density of the material, that is rho is equal to 7800 kg per meter cube, and the E is also given, Young modulus is equal to 200 giganewton per meter square. Okay, find the all the self-weighted load acting upon that particular shaft to find the total what, natural frequency. Okay, that is what fundamental natural frequency of the transverse vibration. Okay, so this is the question. So first you have to note down the given data here. And given data is equal to what, the DO stands for what, the outer diameter is given 60 mm, internal diameter is given 80 mm, and the length is given 1.8 meter, and Young modulus, that is what, the E is equal to 210 to the power of 9 Newton per meter square. Okay, and the density is also given 7800 kg per meter cube. Okay, so this is the given data they given. Okay, so before going to move the further steps, you have to remember this. Okay, self weight of the shaft per unit length formula, we have the mass density into gravitational into area of the cross section. Okay, so you have to put here the mass okay, area of the section of the shaft is equal to what, pi by 4 0.08, that we have to convert this 80 mm into meter and 60 mm into meter. So outer diameter, that is inner diameter minus outer diameter, you are going to get the area of the cross section of the shaft is equal to what, 2.2 into 10 to the power of minus 3 meter cube. So this is about the area of the particular shaft. Okay, and due to this is total overall. Okay, self weight of the shaft per unit length is equal to what, it is denoted by W, that is mass density into the area into, that is gravitational G is equal to area of the cross section. Okay, so this is the formula, we have to remember this. Okay, so in this we calculated what, area is equal to what, pi by 4 outer diameter minus inner diameter, that is maximum minus minimum. Okay, so we got 2.2 into 10 to the power of minus 3 meter square. Okay, so now look at the diagram here. They given here in the diagram, I will explain the diagram only. Okay, so here they one particular hollow shaft is given. Okay, so here the one hollow shaft is given, so 50 kg mass is acting upon that and 60 kg upon acting upon that. Okay, so at a distance of 0.6 and 0.5, and total length of the hollow shaft is 1.8 meter. Okay, so here by considering the one on forces, you have to consider first case, that is 50 kg load, and second consider if 60 kg load. Okay, so first one is if you apply force here, the transfer vibration takes place like this. Okay, that is, okay, again second condition, if you apply the force, you are going to get the transfer vibration like this. Okay, so this is what we got. Okay, so next one is here, moment of inertia of the section of the shaft I is equal to what, pi by 64 d square, it is pi by 64 outer diameter minus inner diameter. Okay, so maximum minus minimum to the power of 4, so you are going to get the I is equal to how much, 1.3744 into 10 to the power of minus 6 to the power of m to the power of 4. Okay, so it is given in the problem number 3. Here in the 3 different loads are acting on this element. Okay, so here three forces are acting on that given beam. Okay, so here 3 forces are acting on this. Okay, so one is 50 kg, second one is a 60 kg, one is a self load. Okay, so here So the natural frequency due to the individual load is calculated by considering the each load acting upon the separately, okay, not individually. Okay, so first one is 50 kg, that is natural frequency for f of n1. So here I wrote here f of n1 is equal to natural frequency of what, load of 50 into, you have to convert into Newton. Okay, so 50 natural frequency for first one, this diagram. Okay, so natural frequency due to load 50 into 9.81, you are going to get 490.5 Newton alone at a distance of 0.56 meter from the left. Okay, again consider from the second diagram the natural frequency, that is f of n2. So natural frequency due to the load 60 into 9.81, you are going to get equal to what, the 588.6 Newton. Okay, along the at a distance of 1.5 from the left hand side. Okay, so again due to these are the two forces acting on that particular component, but we have also one more force is acting, that is the natural frequency of the self weight. Okay, that is uniformly distributed load here. Okay, natural frequency of the due to load self weight, which is considered by uniformly distributed load. So self weight can be equally distributed load. Okay, so here the uniform distributed load will be there. So here all the forces are acting uniformly. We are not going to consider these are 50 kg and 60 kg load. Okay, so that formula, what, uniformly distributed load weight is equal to what, 168.34. okay, so that is the force acting on that particular element. So I wrote here, okay, 168.34 Newton per meter. Okay, so deflection due to the individual loads are to be found out by the find the natural frequency before to calculate the natural frequency. Okay, that is what, before calculating the individual load. Okay, so deflection, so I already given the list of formulae for the simply supported beam, cantilever beam. Okay, so for the uniform distributed load. Okay, so deflection due to the load 490, that is first diagram, 50 kg Newton at a distance of 0.56 from the left hand side. We have the formula, what, delta 1 is equal to load, that is capital W a square b square whole divided by 3EIL. Okay, so a square b square is nothing but what, the distance. Okay, 0.6 and 0.1.2. okay, left hand side, right hand side direction, that is the force acting in the between this midpoint. So I notation here I given delta 1. Okay, delta 1 is equal to 490.5, so 0.6 whole square into 1.2 whole square whole divided by, so here 3 Young modulus is given, moment of inertia we calculated, length is also, total length is 1.8. okay, so delta 1 is equal to deflection due to the load 50 kg, you are going to get 1.713 into 10 to the power of minus 4. okay, so next one is the deflection due to the load, second load at a 60 kg, that is 588.6 Newton at a distance of 1.5 from the left hand side. Again same formula we are going to use, delta 2 is equal to what, W a square b square whole divided by 3EIL. okay, so weight is equal to what, 58.2, that is 588.6 into 1.5 whole square, 1.5 whole square into 0.6 whole square whole divided by 3 into I into, so I into L. So 3 Young modulus is given 200 into 10 to the power of 9 into 1.374. this is the load, that is the moment of inertia. okay, 1.8 substitute by using calculator. So you are going to get what, the deflection due to load delta 2 is equal to 8.03 into 10 to the power of 6 meter. okay, so delta 1 you calculated, delta 2 is calculated. okay, so coming to the last, that is the uniformly distributed load, deflection due to the self weight, which is considered the uniformly distributed load. okay, delta 3 is equal to 5, this is a formula for uniform distributed load. okay, you don't make confuse here. So where you are going to consider here delta 1 delta 2 same formula, whereas here we will consider the delta 3, so uniformly distributed load, so formula going to varies here. okay, delta 3 is equal to 5 WL to the power of 4 whole divided by 384 EI. So this is a formula for the uniform distributed load of the this transfer vibration. okay, so delta 3 is equal to, we write we have 5 into that W is equal to 16, that is uniform distributed load, 1.68 into the power of into 1, what is this is 168.34 into 1.5 into 5. okay, so remaining is 384.5 into, here you have to write here 5, so 5 is missing here. okay, 384 into 200 into 10 to the power of 9 into 1.374 into 10 to the power of minus 6. okay, so delta 3 is equal to 1.675 into 10 to the power of minus 5. okay, so now once you calculated all these values, delta 1 and delta 2 and delta 3, go for finding the natural frequency. okay, overall natural frequency acting on that particular hollow shaft, cylindrical shaft. okay, so according we have to find the number of methods will be there for to find the natural frequency, but here I am going to use the Dunkerley method. okay, so as per the Dunkerley equation, fundamental natural frequency of a vibrating system can be calculated by 1 by f of n whole square is equal to 1 divided by 1 plus f of n whole square plus of 1 divided by f of n 2 whole square plus 1 by f of n s whole square. okay, this is the last one is the self weight, this is a indivisible load. okay, so if you want to find the natural frequency of any particular system, we have the around 8 to 10 methods. okay, so here I am going to use what the Dunkerley equations. okay, so here for the simply supported beam, okay, for simply supported beam we have the formula to find the natural frequency f of n is equal to what? 0.4987 whole divided by square root of delta. Okay, so already we calculated delta. Okay, so that is delta 1, delta 2, delta 3. Okay, this is the formula for the simply supported beam, and this is the formula for self weight. Okay, for simply supported beam, when the self weight is considered, okay, self weight is considered as uniformly distributed load, so f of ns, that is f of ns formula is going to varies, okay, from this to this. So this is I given the list of formula in the table. Okay, f of ns, that is self weight, is equal to 0.5615 whole divided by square root of delta. Okay, so you have to remember this formula. Okay, one formula, second, third. Okay, if it is not having uniformly distributed load, means you are going to use this formula. If you are going to consider the self weight as a uniformly distributed load, then use this formula, that is f of ns. Okay, so now after calculating all those things, so you have to convert first. For the first two cases, you have to use the first formula. F of n1 is equal to what? 0.4985 whole divided by square root of delta 1. So substitute here 0.4985. So delta 1 is equal to we have. So substitute natural frequency for f of n is equal to 38.09. So natural frequency unit is in hertz. Okay. Similarly, you have to calculate the f of n2. Okay. So if you calculate the f of n2, again same formula, 0.4985 whole divided by square root of delta 2. So which is equal to what? Delta 2 value. So you substitute here. So you are going to get f of n2, that is natural frequency for the second load, that is 60 kg load, 55.63 you are going to get. Okay, so last one is to find the natural frequency of the self weighted, that is uniformly distributed load, f of ns is equal to, formula is what? 0.5615 whole divided by square root of delta 3. Okay, so if you substitute delta 3 value, you are going to get what? F of self weight natural frequency is equal to 137.23 hertz. Okay, so this is about finding the natural frequency of the individual element, but we want the overall natural frequency, that is the total natural frequency acting on that particular element. Okay, that particular hollow cylinder. Okay, so formula we have with us, 1 by f of n whole square is equal to 1 by f of n whole square plus 1 by f of n 2 square plus 1 by f of ns whole square. Okay, so this is the natural frequency formula for the, suppose one more force acting means you can go on add addition take. Okay, you can add here. Okay, so we have all the values, f of n1, f of n2, f of ns self weighted. So just to substitute here, you are going to get f of n square is equal to 938.54. Okay, so again f of n is equal to natural frequency, that goes that side, means square root of 938.54. if you make it this square values, finally you are going to get f of n is equal to 30.64 hertz. Okay, so this fundamental natural frequency, the given circular hollow shaft is what? 30.64 hertz. This is your given answer. Okay, so you have to remember in this problem, you have to remember the natural frequency formula, simply supported and self weighted, uniformly distributed load. Okay, if you understand that, so you are going to solve this. Okay, so finding the natural frequency, this is I am going to use one method. Okay, so there are n number of methods will be there. Dunkerley method. Okay, I am using here Dunkerley method. Okay, to find Dunkerley method equation, for this for easy and convenience, you are going to, I am going to use this formula. Okay, so here I covered in this problem, there are different variation load and the uniformly distributed load. Okay, acting on transverse vibration. Okay, this is very important problem. If you solve this one problem, so you are going to understand very clearly. So here these images I taken from this Google images. Okay, so this PP slide. Okay, so I hope you understand this. Okay, so like this you have to remember the formulas, problems on transverse vibration, that is a single loaded, several loaded, uniformly distributed, etc. Okay, so I hope you understand this. Okay, thank you.